Let's get rolling. We'll go through does somebody check my solution? I think it worked. Try it. Looked, because I wrote that on a cell phone. Tuesday was an incredibly bad day. I was very frustrated with Tuesday. Let me give you the story. Now, in hindsight, I almost uncanceled class, but I figured people may have already made plans. It worked out, I would have been available. But around 9 a.m. on Tuesday, I get a call from somebody in Ozaki County, something, the contact tracing something or other. So apparently, I'm thinking it must have been a gas station. So somewhere where I swiped my credit card, there was somebody known to be COVID positive within the 15 minutes that I was swiping my credit card at a gas station while standing outside pumping my gas. So I don't think I had contact with this person, but whatever. So I had to, they already had my appointment set. It was like a 10:25 a.m. appointment. I had to go to drive up, and it's like a 45-minute, the results will be in as early as 45 minutes. What does that mean? So it turned out it was about 45 minutes. So I am negative. So, but that seems to be kind of like overstepping, isn't it? Like there's a point where they say, had I been able to schedule the test myself, then I could have just said class will be online, out of an abundance of caution, right? But and I had to go. It was a thing. And I didn't really argue with them, so I suppose maybe had I pushed harder, it could have been different, but it all sounded very authoritative. Like this is something you don't really have a choice. This is when you should show up and where you should show up. I was not happy that day. Now, having said that, and I don't know if this is going to be the case yet, but there's a event next Thursday, and I'm waiting to hear the time for my presentation because I don't need to be there for other parts, but I may need to, I don't want to cancel class again. So we might need to either schedule a different time, or maybe I'll do class that morning. And if you can't come, I'll record it, but this would be next Thursday if it's a problem. I'll let you know for sure on Tuesday, but any way you cut it, we won't cancel class. We just might have to do a zig around thingy. But we'll figure that out. Hopefully this is a non-issue and we'll just not worry about it, but in any case. I just wanted to throw that out there since I hate missing class, so I don't want that to become a new habit. Okay, so let's go through just so I can explain. I don't want to spend tons of time on it because I think once you see it, it's easier to understand than when you're doing it. The Bidget representation that was due last class. Is that big enough we can see it? Okay, so for what we're looking at for last class, again, we're dealing with abstract data types and thinking about how can we write things in terms of other things that are easily modifiable.
We can't see it on Zoom.
Again?
I'm sorry.
Clancy, is Clancy even on? Hold on.
I'm here.
Did you do your homework assignment?
I sure did. I think I did at least.
No, the one I sent you, the extra one.
Oh yeah, I've been crying over that one for a while.
I haven't got out of bed in 2 days.
I've been bedridden because of how sick I am over this assignment.
All right, you can see the screen now?
Si, senor.
That cheers me up. At least we're back. I don't get angry very often. I was angry Tuesday. That really bothered me. I don't like to not be in control of my own life. Isn't that like frustrating? Although I guess that is kind of like an anti-Christian sentiment. We're supposed to give over to God. Yeah, sinful being, I can't help it, I guess. All right, so the idea here is, so one of the confusions from some of the questions I had is this, the book kind of used an unfortunate notation where they were using a lowercase n for the value that was for successor and predecessor, which was not the same thing as this capital N for what base you're operating off of. If I show you what I mean here, I'll just jump over to this. Yeah, so here's this, so, you know, the inputs to successor and predecessor, these were all n and n plus 1 and those guys. So these guys were, could be confused with this idea of a base of a capital N, which is base 16 was the example they gave. Could be base 22, base 24, base 13. Didn't matter. I should be able to change this guy in my code and it should still operate. All right, so that's the abstract aspect. So now we had to define a constructor called 0, and that constructor just gives us what the representation of a 0 as a bidget looks like, as opposed to a digit. In our numbering system, a 0 is just a 0. But now we have this like list-based format for this bidget numbering system that we write as a list containing a 0. All right. Now the good news for us is, and this goes back to like 200 when we first looked at you know, converting between bases and stuff like that, that a 0 in any base is still a 0. All right. So this will be a 0 regardless of what n is. So this is what 0 looks like. Now, if we did change our definition of how bidgets looked or something like that, we don't have to change our logic. We can just change our primitive types if we implement everything in terms of those primitives. It's kind of the point of using abstract data types. All right, so then we have a test against, is this 0? And you probably noticed that you can't write 0 question mark because it's already taken. It's a built-in thing, so name it something else, where you pass in something that is a bidget, where we know a bidget is a list-based format. So we know it's a 0 if its length is 1 and the car is 0. Okay? So if the length of that bidget is 1 and the car of that bidget is a 0, if both of those things are true, the bidget you passed it is the bidget 0. Okay? So now we get down to successor and predecessor is just the inverse of it. So the whole idea of using successors, and what's kind of funny about this is some, like for instance, Swift has built into it the idea of a successor and a predecessor, and it actually makes you use it for large values. And it's very inconvenient from a coding perspective. You prefer it not to work this way, but at the very least, you kind of can see these things in the wild. But the idea of a successor is it's the value that comes next. So this is one of those problems that's easy to get sucked into when you're trying to think about converting values and things like that that you've done before, going from, you know, a decimal to hexadecimal and things, when really all you're doing is you're manipulating kind of a stopwatch. You know, this thing is counting up, then it zeroes out while we count the next guy up. Then it zeros and so on and so forth. Okay, so successor says, look, if I'm looking at the empty list for my bidget, you know, my bidget has nothing in it, and really this is my stop case. So this has nothing to do with what you would originally pass in. This is how do I do my final time through. Then I'm going to go ahead and return a 1. Chances are that's because I added another column. Okay, so if I'm doing n is equal to 16, I'll count 0, 1, 2, 3, all the way up to 15. But as soon as I hit the 15, that zeroes back out, and I get a new column that's going to be a 1. So this gives me my next column when I have to do that. So otherwise, we're asking the question, have I gotten up to whatever n is? Because once 15 becomes 16, that's when I zero it out and go to the next column, right? So that's what this is asking. If I'm at a 16, given that n is equal to 16, that means I have too many here. So I'll go ahead and cons a 0, my new starting point, onto whatever successor returns for the rest of this digit, which will count up on that next thing, okay? So if the cdr was the empty list, that's where I produce my 1. That's the first time I get that next column, okay? Otherwise, what do? I'll cons 1 plus whatever that dude is. That's assuming I'm not also at an n for that one. But I'll cons 1 plus whatever that guy is onto the rest of my digit, unchanged. Not the successor of it, just unchanged. I only count up in this one column. All right, so that's successor, and you want to, so the successor of 0 is 1. The successor of 1 is 2. The successor of 15 is 0, 1. Successor of that's 16. Successor of that is 1, 1, 2, 1, 3, 1, 4, 1, 15, 1, 0, 2, so on and so forth. All right, and predecessor works basically the same way. We're just counting down, and when we hit zeros, then we have to go and grab from the next column over. All right, so does that make some reasonable sense? So kind of the challenge in this one is wrapping your mind around a problem that you understand as a human, even though you had to think about the digits backwards, as we're kind of reverse lists, but trying to understand it at the what comes next level. Not how do I go from this value to the equivalent in something else, but if I have this, what's the next guy? And what's the guy after that? And what's the guy after that? You were only solving the mini problem of what comes next or what comes before. Does that make sense? When you wanted to solve the bigger problem. It's kind of the what I suspect many of you ran into as you were working on this one. You felt like you wanted to solve this larger problem when it was kind of simpler. It was just a list manipulation type problem. All right, so questions about that before we keep cooking. Go ahead. Probably shouldn't. It probably isn't incorrect. It's kind of like padding with zeros. What does mine give? Yeah, I would say that if I were, it's not incorrect, but it's probably weird. Yeah, the 15-0. Right. So that would have been this. Yeah, you wouldn't have had to do it as a helper function. You could have put the logic right in here. Just asking if it's a 0, just don't call predecessor again, just cut it off. So if the car of this is 0, and -1. Well, yeah, so it would be that. So if this is my countdown right here, I know that I'm going to have a -1. Well, no, I do. I still need to have call the predecessor in case I need to count something else down. You're right. Well, yeah, so any way you cut it, you could do it with a helper function, or you could do it with a let or a let star, which we really haven't looked. Actually, you'd have to do it with a let rec, which we really haven't done yet, but we'll see. Yeah, I see what you're saying. More of a formatting interestingness or something. Yeah, I give this a B+. Garbage. All right. So we've already kind of looked at, well, this is related to what we were just doing. This was the homework assignment. We've already looked at the environment interface with empty env, apply env, extend env, right? Or at least we started that, but we haven't done the like extend env with more than one parameter. Okay, you know, because realistically we might want to say a equals 7, b equals 6, and add those into one level of our environment instead of having to do that 2 separate times to extend our environment if we're trying to move towards scoping. Let me see where we're going with that. Okay, so I think we've pretty much written this in our code where we have this idea of an empty environment, which just returns the list empty env. We have the idea of it extending an environment that takes exactly one variable, it's a corresponding value, and the environment that we're extending. And that gives us a list called extend env with the variable, the value, and the environment. And then we have apply env, which allows us to look up a variable in the environment or return a false maybe if it wasn't found. One thing that you'll find here, I think advanced student supports it. I don't use them at all in any of my code, but they're showing this essentials of programming language error message thing that's built in. But we don't write errors in our codes. We don't error check. It's a bad programming practice, but if we're focused on the language construct aspects of this, I think that's reasonable. All right, so what we're left with here after we're looking at this environment interface is an idea of something that we can sort of see that we have some scoping weaknesses where like, hey, if I'm gonna be, you know, if I imagine what things are gonna look like in, you know, 3 weeks or something like that when we were starting to deal with functions and my interpreter does something real, not just have variables, right? All of a sudden scoping might become more important. That's something that we kind of take for granted in our modern programming languages, and we certainly should have that. And we can look at our current variable environment here and kind of say, I'm not sure this guy gets us all the way. This can certainly have some weaknesses. But maybe the step that comes before that is the idea of saying, sometimes I want to define several variables in an environment, especially with a starting environment, if I want to kind of give myself a, you know, 3 or 4 different variables to test with when we start testing our interpreter. Because the first interpreter, I think I mentioned it because I would have probably brought it up on this slide, is we're going to be doing what's called an environment passing interpreter, where we always have to have the current status of the variables that we have access to. We pass the scope around. So the starting point then is if I want to test stuff on my with my interpreter, it might be in my best interest to have a starter environment that has a couple of variables that I can operate on in it. And it could be inconvenient if I want to have 7 or 8 variables that I have to do this extend of the extend of the extend of the extend to get my variables in there. So it might be kind of nice if I can have like kind of a super version of extend env that kind of does it for me. So we'll look at that. That's probably, I'm guessing, on this next slide thing here. Okay. So we already have this idea of has binding. So let's just look at our code here real quick. Is this? We did write an environment, didn't we? we'll steal this because I think this was an older written one. Actually, did we write get name and those things? Right, but did we have these getters for these things? Okay. Okay, so then what I'm going to do is just to give us our clean starting point for our interpreter. I'm going to copy this and we're going to put this in a we're going to save this as CSC470 interpreter 1. Okay, so just to kind of go through this again real quick, we have a constructor for our empty environment. We have a constructor for an extended environment that takes a single variable, a single value, and the environment we're extending. And these are just data, this just creates a data structure, a list formatted data structure. We have a getter that, given an environment, will get the name associated with that, with the variable of that environment. We have a get value, given an environment, it'll get the value associated with that name. Get env will give us the extended the environment in which we're extending. We have a test whether something's the empty environment. And then we have the idea of this apply env. And apply env takes in the variable name we're looking for and the environment in which we're looking for it. Nailed it. All right, so, and you know, if we've run out of places to look, we return a false. Otherwise, if the name we're currently looking for is the name we're interested in, we'll return the value. Otherwise, we call apply env on the extended environment. Okay, so pretty straightforward. Now, we might want to have constructors, actually, has binding. So they want us to have some additional tests, like a predicate for has binding, that effectively, well, here, let's go this route. So if I say define, actually, we'll put this beneath it. Has binding. Has binding is a lambda that's going to take in a var name and an environment. And what should has binding return? How can we write has binding? Has binding is going to return true if the variable name we passed in is bound in the environment and false otherwise. Take 3 minutes and try to write this.
Would you be able to post the code to Slack so that we could have that starting point?
No?
Okay, cool.
Thank you. All right, give me a second. It's up there. All right, so let's look at this. Hopefully you thought to implement this in terms of apply env. Because really, has binding is going to return true if apply env gives me anything but false. Right? So we're going to say not equal apply env var name env false. If I try to apply it, I get something not equal to false. That means it was bound. I found it. Okay? So the more times we can implement things in terms of other things, we reduce the number of places we need to change stuff. And that's going to be handy, especially as we're going to have kind of an evolving interpreter here, where we're going to work on something, hit a point where it's like, okay, well, this works, this works, this works, and all of a sudden we're like, you know, I really want this programming construct to work this way, and we realize that, oh, our environment doesn't really support that very well as written. We need to do something. You don't want to have to reinvent, pull apart the whole engine just to change one little thing. All right, so that should be has binding. We're going to return whether, well, we're going to check to see if apply env is equal to false. If it is, that means it's not in there. We want to return not that. So it'd be true if it's in there, false if it's not. And this is one nice thing with scheme and also I suppose it's fair to say interpreted languages, is that we know that with apply env, we could get a real value, probably a number. Right now we're thinking about storing, name value pairs. It's a variable name associated with a number, or we get a false. We don't have to worry about, how equal is applied here. I'm saying, is this value equivalent to this value? So if I go ahead and I give myself a, define env to be an extend env A5, extend env B7, empty env. Just make sure that gives me what I expect it to give me. Is it called empty env? Empty dash env, empty. Extend env requires me to give it a name, a value, and an environment. Extend env, name, value. Here's the environment, extend env, name, value, and environment. My constructor for empty env. Oh, this is actually written poorly, because this really should be a lambda that takes no parameters and boils down to that, or the list containing empty env. That might be the way I would write it this time around. The list containing empty env. All right, so there's our A5, B7, and then our empty environment. All right, so now we should be able to test like has binding of A and get a true. I need to give it my environment. Has binding A and env, and I get a true. Has binding C, E, and V, and I should get a false. All right, so now we have a way of specifically asking, is something available in my environment? Maybe that's something that's helpful, maybe it's not, okay? But I can say we just saw by example that creating your starting environment is a little bit rough. So it would be nice if I can kind of stack variables on top of each other and get more variables at once into my environment. So we have this idea of adding to the environment interface a constructor called extend env star that, you know, it's using a list representation. So we have a bunch of variable names, a bunch of variable values, and the environment we're extending. And it produces the beefed up version of that environment. Now, we might be enticed here to say, well, why don't we actually increase or improve our variable environment by allowing it to hold multiple name value pairs at the same level? But we can say, I'm not sure we really gain very much. We've already written this thing up to this point. So what they really want to let us do is say something like, extend env star lets me take in a list of C, D, E, and of values of 1, 2, 3, and then my environment, and extend it that way. So it automatically gives me C equals 1, D equals 2, E equals 3 in my environment, and it uses my current environment constructs to do this. That make sense? What we're trying to accomplish here? But we should, as of right now at least, we're going to say this environment interface works fine. And I already have these other constructs that work on it. Applying env has binding. So why change my format when, as far as I'm concerned right now, we haven't hit stuff that breaks it? It's just a little inconvenient for me to create an environment with lots of variables. So we want to go ahead and define a extend env. That's going to be a lambda that's going to take in a list of names, a list of values, and the environment that we're extending. List of names, list of values, and it should then extend this environment using our current tools for extend env and so on and so forth to give us this extended environment. So I'll move this up top here just so you can see how I'm intending for you to call it. This is extend env star. All right, so I intend to call it this way by allowing me to create a whole bunch of name value pairs at once, but it's going to do that in terms of your normal extend env and empty env using the built-in constructors we already have. All right, so take a couple minutes and try to write extend env star in terms of extend env. We're not reinventing our data structure. We're just giving ourselves a convenience function for using our existing data structure. Make sense? Okay, so let's look at this guy. So extend DNV star. We wanted to process through our two lists. We know that these lists are equal length. We can make that assumption, right? Otherwise, they're calling it incorrectly. So as we're writing this, we know that we are building up an environment, correct? The environment we're starting with is our ENV, and we're going to continue to call extend ENV on these guys until these lists are empty. As soon as they're empty, we're done. So we'll have our cond. Actually, we already have a empty ENV test on our environment. Actually, that's not what we're testing here. We're saying if null list of numbers or list of values, either one of those, then boil down to our environment. That's our final answer. Otherwise, if we're not null, no, so we could have done this as an if, then what we want to do is we want to call extend ENV on the car of list of numbers, the car of list of values, and our current, well, I'm going to say our current environment, but we're not ready for the current environment. And then whatever is returned by extend ENV star on the cooter of list of names, the cooter of list of values, and our current environment. So extend ENV star is going to take two lists of the same length. If we're out of stuff, just return the environment we were looking for. If we're not out of stuff, then we want to extend our environment using our normal extend with a name value pair, so the car of each of those lists. And what environment are we extending? We're extending the environment left from calling extend ENV on the rest of my list of names, the rest of my list of values, and the environment I've been passing along. Keeping in mind that this guy, actually, you know what? This is, I'm going to write this differently. I'm going to actually call extend ENV star. It'll actually create them backwards, but that's okay. So extend ENV star, I'm going to pass in the cooter of my list of names, the cooter of my list of values, and then the new environment is going to be the extend ENV of the car list of names, the car list of values, and the environment that was provided to me. So I'll call extend ENV star on the rest of those lists, and the environment that I'm extending is going to be the singly extended environment of my car list of numbers and list of values and whatever environment was originally passed in. That's going to be the new environment that gets passed in to extend ENV. This should then allow me to do something like this, which should give me an A is 5, a B is 7, and then these other guys in there. So there's the E is 3, D is 2, C is 1, so it built them backwards. And then A is 5, B is 7. All right, that makes some sense? Now, one thing that we already wrote this kind of better than the book's ordered. You kind of saw what I had from this this old one here. where our empty environment was not written as a lambda, it was written as a hard-coded list. So the book talks about a procedural representation of these guys as being an upgrade. Writing them in terms of procedures says you can call that function, and the function will produce what it's supposed to produce, whatever that is. We've already written ours that way. So ours is already written in a better way. Now, to kind of drill this point home, the next thing the book has you do, and something that would be a homework assignment, but I want to skip past since we weren't in class on Tuesday, is this idea of a stack data structure. What's a stack? Remind me, what are the functions of a stack? Push, pop, peek. So push puts something onto the stack. Pop removes something from the stack. And then peek lets you see what's on the top of the stack. Really effectively, the two functions are push and pop. Peek is like a convenience function. So if we were to create, so like right now we just implemented the constructors and the helpers for our environment interface. What if we were doing something similar for a stack interface? How do we construct the empty stack? So if I were to write a function, define empty stack to be a lambda that takes no parameters, what is the empty stack? Or what could the empty stack be? How do you want to represent a stack that has nothing in it? Empty list? Reasonable enough? I mean, we certainly could you know, put the word empty stack in there or something like that, but maybe empty list works out well because then we can ask null about it. Okay, so then we want to define push, and push is going to be a lambda that takes in a val and a stack, and we push that element onto the stack. Well, what does that look like? How do we push val onto the stack? Well, stack, we've decided, is already a list format, right? So we're representing our stacks as a list, and we probably want the front of the list, the car of the list is the top of the stack. Sound reasonable enough? Okay, so if I want to add something onto a list, I'm going to be building a new list, so we're going to be consing, right? So we're going to cons val onto stack. Pretty simple construct, right? And what about pop? Pop is a lambda that takes in a stack. And what is its job? What do we want pop to do? Okay, so it gives us the first element of the stack. Historically, we would also say it should change the stack. So what you sort of kind of end up with is I have two choices here, right? I can have pop return the car of the stack, which would be reasonable. I can have pop return the modified stack, which would also be reasonable. But what if I want the value in the modified stack? So what I'm saying here is I can just say, oh, I'll just return the car of stack. That's reasonable. I could also say define pop2 to be a lambda that takes in a stack, and it boils down to the coder of my stack. That is everything but the top. Well, potentially. So that then gives us a differentiating factor between peak and pop, where historically peak says, here's the top of the stack, but not removed. Pop says, here's the top of the stack, and it has been removed. What's our limiting factor here? What aren't we able to do that we wish we could do? This kind of connects to this idea of an environment passing interpreter. Why do we need to pass our environment around? And we don't have the ability to have a global variable, or at least don't know about it at this point. So it would be nice for us to say, here's the updated version of the stack. We've updated our variable, and then here's the value that you wanted. Because of the way state works inside of Scheme, we kind of have to pass things around. So if we assume that we still don't have the ability to, if we assume we still don't have the ability to return our, or to change the value of our stack, we're passing the stack around, then how could I implement pop? Let's call it pop 3, such that it gives me both the value I popped and the updated stack. Okay, yeah, we can just invent a data structure that is the combo deal, right? Here you get a list that has your first value, so something like define pop3 to be a lambda that takes in a stack, and what we're going to do is we're going to return a list whose first value is the car of that stack and whose second value is the coder of that stack. And now we have a to list that has the multiple things in it. But now we don't have the ability to pop multiple times. How do we handle that? So our limitation is this environment type thing. Now I'm going to show you something you can do that's not going to be, I'm more academically showing it to you. You probably don't want to try to use it in your code yet. So what I'm going to do here is we're going to create kind of what you called as a global variable. So I'm going to say define, we're going to call this guy last pop. All right. And initially last pop is going to be, I don't know, do we even need to, I'll just start off as false. No, there's no value in there. Now, when we write pop, we're ultimately going to have pop boil down to the popped value of our, let me write it this way. We'll just write pop. We want it to boil down to the coder of our stack. That way we can push, 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 pop, pop, and have a modified stack. So let's just kind of look at that. So we're going to say we want to pop the pop of the push of 1 onto the push of 2 onto the push of 3 onto the empty stack. Okay, so this will be the stack with a 3 on top, with a 2 on top, with a 1 on top, and then it's going to get rid of the 1, get rid of the 2. So we should just have the stack that has a 3 in it when all is said and done there. Okay, so that is our ability to now move through those things. Now, just to give you the starting point for this, I'm going to say set bang, what's it called? Last pop to be 5. And what I'll go ahead and do is I'll print out last pop here, and I'll print out last pop after that. We defined the last pop right here is false. And then we called, oh yeah, then we have set bang here. And notice that set bang is a function that boils down to a value. The value it boiled down to is void. It returned nothing, but it did something. It allowed us to update the value of a variable. So set bang here updates an existing variable with a new value. This is in Scheme's environment, not our environment. we're going to ultimately implement our own version of something like this down the line a little bit. But for right now, we can look at this and say, well, I can kind of fake it now. I can say, you know what? I want to update my environment with I want to have access to the last popped value. But I also want to be able to call pop, pop, push, push, push for my stack and be able to have my stack be able to dynamically update like that. So now we can sort of kind of have both. I can write, now that we have this new function, which again, I'm warning you, don't use very often. You're going to see why here in a second. It's not going to really help us for a while, but it is kind of a get out of jail free card sometimes. So if I have this pop function and I want to ultimately store the last pop in last pop, but also boil down to my adjusted stack, how might we accomplish that? So I want two things to happen here. For pop, I want to have my final result be my adjusted stack. But I also want to have the option of looking at last pop and seeing what was the last value we popped in the event that I'm interested in that. Knowing that set bang gives us a void. So we certainly don't want void being put out on the screen. So what if I did something like this? What if I said set bang last pop is the car of stack? Oh, hold on. This pop, pop, push, push thing won't work right now. So we'll do a single pop. That should work. So that's what it boiled down to, is just a void. But that's okay, because that's all I did in there was the set bang. What if I created a list out of that void? Now I have a list containing my void. And then what if I had a list created out of the cooter of my stack? That's what's left over, right? Now I have my list containing what's left over in my void. And then I return the car of that list. So now I have what's left over, but I also have my last pop, which should be my 1. So you see how we can kind of sort of manipulate it to pull off some things we want. So just to kind of show what just happened there. What pop is doing is it's ultimately updating our variable last pop to be the value we just popped. But all functions in Scheme boil down to a value, even if that value is nothing. We've been used to Java, for instance, we say it returns nothing, so it's void. No problem, no harm, no foul. All right, so with that in mind, we have this idea that, well, I kind of want both things to happen. I want my resulting updated stack, but I also want to have my last pop available to me. So now I can do a pop pop and pull that off. I'll lose access to that 1, but I'll get the 2 in my last pop. So there's my secondary pop, and this is the last value that it did pop. That make sense? Okay. Now, what if I wanted to have a collection of all the values I popped? I could actually treat my last pop as a stack, couldn't I? We keep pushing stuff onto the stack. So in any case, this is a little bit of a cheat thing with this function called setBang. SetBang says update a defined value. But as I said, something you're probably not going to use very often, but something that does exist. But the real purpose of looking at this right now is to see that all functions boil down to a value, even if that value is void. And that will sometimes give you problems that you need to come up with creative solutions for. Okay. That was our stack. So now I think we're on to the interpreter. Okay. So again, we have our, in fact, let me just grab this guy since now we have things that have names. So we're kind of putting together our sandwich that we've been working on. So here's our grammar. Again, it's our simplified grammar that only allows us to have one identifier here. Just so happens though, we just created an extend env star that would allow us to do multiple bindings. Could be handy when we want to expand on our lambda that takes more than one parameter or 0 parameters for that matter. So in any case, we're back to our old grammar here, but now we're starting to give names to them. Meaning, what is this guy? So we have a var expression, a lambda expression, an app expression. We want to have constructors for creating these kinds of expressions. This is the grammar of the lambda calculus expression. Each of these productions is a way that a lambda calculus expression can exist. We want to have ways of constructing lambda calculus expressions using, following this grammar, but using our constructors. Why? In case our grammar changes, we can update the constructors and we don't have to change the rest of our interpreter, right? We can update this grammar and the thing that will change will be our constructors and our getters. All right, so we'll go in here and I'm gonna just get rid of the, I'll throw this on Slack real quick because I'm about to dump it. Call that setBang examples with stacks. Okay, so effectively, this is our environment initializers. This allows us to work with our environment. And now we want to have our grammar constructors. All right, our lambda calculus expressions currently have 3 forms. We're going to call the first form, well, I can show it either way. This guy, this identifier, is a var expression. That is how, I mean, if we were just looking at a Java program, we saw I, we saw A, we would say, ah, that's a variable name, I need to resolve that. The I need to resolve it part is what do we do with var expressions? The how do I construct it part is what we're building right now. The constructor for a var expression. So we're going to create define a var exp. And again, we're doing this in lambda formats, right? So procedural format is what the book would call it. So we're going to have a lambda that takes in a single symbol. And this guy is going to boil down to a list that I'm going to go ahead and label them with var expressions. I think Sarah had asked something about that a couple classes ago, right? Like, is it okay to label it with something versus not label? Completely okay. And we can say that, oh, labeling it with var expression is kind of extra verbose, and we're going to have to, do extra work to get rid of that kind of needless metadata. So if we're talking about this in like, technology terms, we would call this metadata. All right. But if I return a list of var expression and s, we can say that's a little bit cumbersome. But if I'm writing getters to work with my constructors, it doesn't matter. I can nicely identify it like this. So things are kind of more verbose, but kind of spell themselves out, right? And then I can just have my getters get me the getter. Give me the actual meat of what we're dealing with, but don't take away my metadata that helps the human look at it and give some meaning. So this gives us kind of the best of both worlds, especially if we're not worried about how long the code is or something like that. Okie dokie. So that's our constructor for our var expression. Next guy is what, a lambda expression? So a lambda expression, this guy needs to be, we have a lambda calculus expression, and we have a identifier that we're going to keep track of. We can have predicates associated with these things as well. We'll go ahead and write these. So if I'm building, this is my constructor for a lambda expression. Excuse me. Define a lambda expression to be a lambda. Now, this guy requires multiple components to build a lambda expression. A lambda expression has an identifier. Right now, it has just a single identifier. As you kind of fast forward a little bit, this constructor is going to become a little bit more interesting, but right now, simple. So it's going to take in a single identifier, and it's going to take another lambda calculus expression. So this is going to be a lambda that's going to take in a symbol as well as a lambda calculus expression. And it's going to build a list, maybe lambda exp, with that symbol and my lambda calculus expression, something along those lines. All right. So again, this kind of starts feeling like this is pretty verbose. We're spending a lot of time doing these little stupid constructors, but it's going to make our life easier when we go to start building, writing our syntax for our language. So last one is an app expression. And we look at app expression. App expression is a list containing 2. Right now, it's exactly 2. But as you might imagine, if we start allowing, so how are lambda expressions called? Lambda expressions are called using an app expression, right? Where the first element here is the lambda, and the second element here is the single parameter being passed in for this identifier. So if I change my meaning for a lambda expression here to allow for more than one identifier, more than one parameter, right? That's what the identifiers are for a lambda. That's a procedure. Those are the number of parameters. So if I change this to allow for 0 or more parameters, my definition for app expression must also change. Because now it's the car is my lambda. The coulder is all my inputs that need to be bound to all of the identifiers in my lambda. Make sense? Okay, so not difficult, but has consequence when we make that change. And it's going to be easier for us to deal with those consequences if we're dealing with it at the constructor level and the getter level. We can update those things so that our interpreter doesn't break. All right, so an app expression is going to be a lambda that's going to take in a lambda calculus expression. And actually, I'm going to specifically call this guy a lambda exp, because that is what we expect. An app expression, it's a sandwich that starts off with a lambda expression and then creates bindings for the rest of the stuff. Right now, it creates a single binding, exactly one binding. So it's going to take that and really it's a value that will be associated with a symbol, right? So if we're trying to keep this kind of really match it to language stuff, we're going to call this param value. I think that starts sounding close to what languages should sound like. So this is going to be a lambda that's going to take in 2 parameters. The first parameter is going to be a lambda expression. The second parameter is going to be a value associated with the parameter that that lambda expression is expecting, the single parameter. And we'll go ahead and create a list here, call it an app expression, along with our lambda expression, along with our param value. All right, so that's all our constructors for our grammar. That allows us to create our 3 different productions. And if we start adding more productions, like we'll have one for an if statement and a loop and stuff like that, we'll be able to add them here. All right, so now we can write predicates for these. Predicates are pretty easy, right? Grammar predicates. It's extra easy the way we've written it right now, right? Because we have things at the beginning of it. So if I say define a var exp, a little question mark there, that's our predicate, and this guy is going to be a lambda that's going to take in some lambda calculus expression. Lambda. What's it going to return? It's going to return whether or not equal car lambda calculus expression. We know it's a list, right? Why? Because we know all of our constructors are lists. Now, I'm going to actually write some getters for this just to keep it as simple as possible. Except the direction of the book's extractors, yeah. Let's write these extractors first before we write the predicates. All right, now one of the extractors that we have that the book won't necessarily have is the type. Eventually the book is going to introduce types into our language, like int type versus number type versus char type, Boolean type, that kind of stuff. But we're looking at an extractor that tells us the label of this kind of lambda calculus expression. So we're going to go ahead and what's the format that they're using? Like a weird arrow looking thing. So we're going to have an expression to type. So define EX, let's do it, lambda calculus expression to type. Something along those lines. And this will be a lambda that takes in a lambda calculus expression. And what it's going to return is the car of that lambda calculus expression. And this works because we've defined all our lambda calculus expressions to have the first value that is a word, right? It's a symbol that's either, you know, lambda expression, app expression, var expression. So this will allow us to extract that. Then we start thinking about the other things we might want to extract. So we will have a define var exp to call it var name. That's what we're getting out of that var exp is the variable name. And this will be a lambda that's going to take in a lambda calculus expression that we actually, let's write it so it's going to take in a var expression. Specifically, that's the type we would use on the extractor. And we want to return the catter of our var exp, because that's how it currently works. The variable name is the catter of that list right there. Time are we out? 35? 25? Oh, well, that's actually good. It's perfect. All right. So for our homework, and I'll post this up on Slack, but for our homework, finish writing the extractors and predicates for our simple grammar. C Slack for current code. Make sense? So you're going to finish writing what I just started writing. We got the type from this guy. Var expression of our name is going to be that. So for Lambda expression, the extractor will allow us to get the Lambda calculus expression and the symbol. Those are the two pieces of information we're extracting from that. So if I have something that's a Lambda expression, the two pieces that I might want to get from that is the symbol that I'm binding and the Lambda calculus expression in which I'm executing the code. If I'm dealing with an app expression, I want to get the operator and the operand. That's out of those. Okay, so these are getters that allow you to operate with those. And then the predicates will be, they should be simple. They're all the same. Is the car the word that we're looking for? Okay, so questions, comments, concerns, bribes. All right, I will see everybody on Tuesday, and I think I got a note that says we'll have to figure out an alternate time for class on Thursday next week, but we'll figure that out on Tuesday. But we won't cancel class. We are going to figure it out one way or another. Slack. Code for homework.